You know that feeling, right? You flip the page in your physics exam and your heart just sinks. The question looks like it's from another planet. Well, you are definitely not alone. In this explainer, we're going to decode a real exam question and turn all that confusion into pure confidence.
And we're not just talking about some abstract theory here. No, we're going deep inside a real question from an official AQA higher tier paper. This is the real deal. And the strategies we're about to uncover, you can use them in your actual exams.
So that's our mission today. This isn't about just memorizing a bunch of formulas. It's about learning a method, a system, for decoding any question the exam decides to throw at you. And trust me, by the end of this, you'll see that even the most intimidating questions are really just a series of simple, manageable steps.
So here's our flight plan. We'll kick things off by introducing our case study question. Then we'll deconstruct it piece by piece. We'll apply the physics, get a grip on the data and graphs, and then wrap it all up with a winning strategy you can take into any exam hall. Let's jump in.
Okay, first up, let's meet our challenge for today. We are diving headfirst into question 2 from this paper, and we picked this one for a very specific reason. It's a perfect example of how examiners love to test multiple skills all in one go.
So why this question about an airplane? Well, because it's got the whole shebang. There's a scale diagram, there are forces, there's motion, and, yup, graph interpretation. It's basically a mini physics exam all packed into one question, which is perfect for what we need to do.
All right, now this is absolutely the most critical part of the whole process, seriously. Before you even think about reaching for a formula, you have to put on your detective hat and figure out what on earth the question is actually asking you to do. You know, the first thing examiners are checking for is just, are you paying attention? It's so easy to just look at the plane's flight path and move on. But the most important clue on this whole diagram is hiding in plain sight, right at the bottom, the scale. 1 centimeter represents 70 meters. That little piece of text is the key to getting the first marks. So, rule 1, never, ever ignore the diagrams. So, here's our first task. And you've got to notice the specific language they use. See that word displacement? Examiners absolutely love that word because it's not the same as distance. We're not supposed to measure the winding path the plane actually flew. Nope. They want the straight line journey, as the crow flies, from start to finish. Let's break this down. Determine is just a fancy exam word for calculate or work it out. We already know displacement means the straight line distance, and magnitude, that just means they want the number, the size of it, not the direction. So the plan is super simple. You take your ruler, you measure the straight line from the start point to the finish point, and you'll find it's 6.5 centimeters. Then you use that magic scale we found earlier, just do 6.5 centimeters times 70 meters for each centimeter, and you get 455 meters. That's it. That's your answer.
See, once you know what they're asking, it's time to open up that physics toolbox in your brain. Let's move on to the next part of this problem and see how these ideas start to connect and build on each other.
And just like that, the exam switches gears. We're moving from motion to forces. This new diagram is great. It gives us all the numbers we're going to need. We've got a forward thrust from the engines, and then 2 forces fighting against it, air resistance and friction.
The key concept we need here is resultant force. It sounds complicated, but it's really not. It's just the overall force once you've added everything up. Think of it like a game of tug of war. You add up all the forces pulling one way, and you subtract all the forces pulling the other way. So let's just apply that idea. We've got 14,000 newtons of thrust pushing the plane forward. Okay, now, what's pushing it backward? Well, we have to add the 2 backward forces together. That's 4,500 newtons of air resistance plus 9,500 newtons of friction. And what does that give you? A total of 14,000 newtons backward. So wait a minute, 14,000 forward, 14,000 backward, that means the resultant force is 0. And this is where they link the questions together to see if you're really thinking. Part 2.3 asks you what this means for the plane's motion. Now, because the resultant force is 0, there's a huge trap here to just say it's stopped. But you've got to remember Newton's first law. An object in motion stays in motion at the same speed and direction unless a new unbalanced force acts on it. So since the forces are balanced, the plane is simply moving at a constant velocity. And for the marks, the official mark scheme says they'll accept either constant speed or constant velocity.
All right, let's tackle what can be the final frontier for a lot of students, graphs. I know, but examiners love them because they're a fantastic way to see if you can visualize the principles of physics.
So here's the challenge in question 2.5. We get a distance time graph, and our job is to draw the velocity time graph that tells the same story. The absolute number one key to this is remembering what the gradient, the slope or the steepness of the line, actually represents on each type of graph.
Okay, so on a distance time graph, the gradient is the velocity. So let's read the story. In the first section, the line is totally horizontal. A flat line has a gradient of 0, which means 0 velocity. So far, so good. Then, in the second section, the line is a curve that gets steeper and steeper. A steeper slope means a higher velocity, so the plane is accelerating, and because it's a nice, smooth curve, that tells us it's a constant acceleration. So how do we draw that? On our velocity time graph, we start with a horizontal line right on the 0 axis, and then it becomes a straight, diagonal line sloping upwards, showing that velocity increasing at a steady rate.
Let's check out the next data challenge. This graph is showing atmospheric pressure against height. Now, the very first thing that should jump out at you is that it's not a straight line. It's a curve, and that's a huge clue that the relationship isn't linear. As the height goes up, the pressure goes down, sure, but look at how it's curving. The rate of the drop is slowing down.
The key word here, and it's a gift, is estimate. The graph data actually stops before 10 kilometers. So to solve this, you have to do something called extrapolation, which is just a fancy way of saying continue the line. Follow the trend you can already see. It's clearly flattening out, right? So just carefully sketch a little bit more of that curve until you get to the 10-kilometer mark, then read the value across on the other axis. Now, the mark scheme is pretty generous here. They'll accept any answer between 26 and 30 kilopascals, so as long as your estimate is careful and sensible, you'll get the marks.
So there you have it. We took a big, complex, multi-part question and broke it down into these small, manageable chunks. So let's just pull all of that together into a simple, powerful strategy that you can use every single time. Here it is, your 3-step game plan for exam success. First, you play detective. Deconstruct the question, hunt for those key words, and squeeze every drop of information out of the diagrams. Second, you be the physicist. Connect what the question is asking to the core physics principles you've learned. And third, you become a data analyst. Read and interpret those graphs with confidence.
And that really is the secret. An exam question isn't one giant, terrifying monster. It's actually just a collection of small, solvable puzzles. And if you approach it with this method, you can tackle them one by one and build your way to an amazing score.
And one final thought to leave you with. This process, breaking down a complex problem, looking for the evidence, applying fundamental principles, that's not just a skill for passing physics exams. That's a skill for life. So the real question is, where are you going to use it next?